This is the 555 timer, probably the most famous and used integrated circuit. In this video, I will show you how to assemble an astable pulse generator with it and how to configure the frequency from a graphic method instead of the arithmetic one. The 555 timer was invented by Hans R. Kamensen in 1971 while he was working at Signetics Corporation. The chip quickly became popular due to its simplicity, versatility, and low cost. It is now one of the most widely used integrated circuits in the world. If you would like to learn more about how this IC works, you can see this great video from Element 14. For our assembly, I'll be using the diagram from Texas Instruments, included in the datasheet, and an implementation on Breadboard. On page 15, there is a recommendation to include bypass capacitors, or, for this purpose, decoupling capacitors at the DC input, which there should be placed close to the integrated circuit. So I will add it here in this diagram. You can see my previous video about decoupling capacitors that explains their importance. Now let's go ahead and assemble the circuit. For this project, we'll need a few components, including a 555 timer chip, breadboard, resistors, capacitors, potentiometers, and connecting wires. This is pin 1 to ground, pin 8 to VCC, pin 4 or reset to VCC, pin 2 to pin 6, pin 3 is the main output. In this case, we'll use an LED with a 330 ohm resistor. For this exercise, I'm not using the complementary load. Okay, pin 5 with a 0.01 microfarad capacitor or 103 ceramic capacitor to ground. Decoupling capacitors. This is 104 ceramic and 1 microfarad electrolytic capacitors between pin 1 and 8. Those should be placed as close as possible to the chip. Resistor A between pin 7 and VCC. Resistor B between pin 6 and 7. Capacitor C between pin 2 and ground. Now powering the circuit with 5 volts DC. Wow, it is working! And this is how it would look like if we added the complementary load. Now it is time to use the oscilloscope to analyze the frequency. And for that, I'm turning on frequency and duty cycle measurements on the oscilloscope. We are having 1.4 Hz. But how can we adjust the frequency? We can use resistor A, B, and the capacitor C. I want to be close to a duty cycle of 50%, or the proportion of active or high state divided by the whole cycle. This is to get a symmetric and nice squared wave. This formula on page 11 says that to get close to 50%, RA should be as small as possible, but cannot be 0, otherwise the circuit will not oscillate. For this exercise, I will use 220 ohms for resistor A. Even though frequency can be calculated with this formula, that is on the same page of the datasheet, for this video I will use a graphical method instead of arithmetic. So let's look at the chart on the same page 11. The horizontal axis shows the frequency, which is what we want to reach, while the vertical one is the value with the capacitor in microfarads. Diagonal lines show the sum of resistor A plus 2 times resistor B. Remember that RA is 220 ohms, so we can play only with resistor B, which should be approximately half of the value of each line. Let's say we want 10 Hz. We have 4 options: almost 5, starting with a capacitor at 0.01 microfarads, which is this 103 ceramic capacitor. Then our resistor B should be close to 50 mega ohms. But I don't have such value, so let's move to the option 2. Now with 0.1 microfarads, which is this 104 ceramic capacitor, the resistor B should be close to 0.5 mega ohms or 500 kilo ohms. Closest I have is this 470 kilo ohms. Okay, let's try it. Oh, great! Okay, now it blinks faster, and the oscilloscope shows 14 Hz. It's close but not accurate. This is because of the resistor value, but also because of the diagonal line that doesn't cross exactly at 10 Hz. The duty cycle is 47%, close to what we expected. Now let's try 100 kHz. I'm choosing this line of 1 kilo ohms, with the previous capacitor 103. This time our resistor B should be close to 0.5 kilo ohms, or 500 ohms. The one I have is 510 ohms, which should work fine. LED appears to be on all the time, because it is blinking so fast that I cannot see when it is off. Oscilloscope shows 87 kHz, which is not exactly close to 100 kHz. This is in part because of the resistor value, the accuracy of the capacitor, and the diagonal line from the chart that doesn't cross exactly at 100 kHz. The duty cycle is 53%. For a more precise configuration of a particular frequency, we could use trim pots, potentiometers, or presets to get the right resistance value. I recommend to use ranges that are close to the value that you are looking for. Also, there are several calculators online to get the right value you need. Just Google it and you will find some. For example, this one from DigiKey. Just select the tab as table, where R1 is RA, R2 is RB, and C1 is C, where the calculated value for 14 Hz was 220 ohms, 470 kilo ohms, and 0.1 microfarads, giving 15 Hz. Very close, perfect. However, for 100 kHz, this is not working accurately. Calculated frequency with value from real components is 116 kHz, while in the circuit we got 87 kHz. This is an error of 25%, and I don't have an answer for this, just to remind us that we were close or outside of the chart for frequency calculations according to the manufacturer. It looks like we were close to the limit. But can this circuit run faster? I mean, produce a higher frequency? The spoiler is yes. However, there is a price to be paid for that. And for that, I will publish another video just to talk about the maximum frequency, so stay tuned. But now you know how to connect the 555 timer to generate a square signal at any frequency you want. Thanks for watching this video. Knock knock, instead of the arithmetic one. By the whole cycle. Even though chart on 470 kilo ohms, 160 for frequency calculations,